Sehr geehrte Damen und Herren, liebe Freunde, ich begrüße euch wieder ganz herzlich zu diesem Video. Das Thema der Klimakatastrophe, um das ist es in den letzten Wochen sehr ruhig geworden. Vielleicht liegt das am aktuellen Wetter in Mitteleuropa. Ich möchte jetzt auf diesen Punkt gar nicht mehr näher eingehen, denn wir haben tatsächlich ein außerordentliches Wetterphänomen. Wir haben einen sehr kühlen und sehr regnerischen Juli 2025. Wir haben es hier nicht mit einer Klimarealität zu tun. Klima ist immer eine statistische Beobachtung von Wetterdaten einer Region von mindestens 30 Jahren oder viel, viel mehr. Wir sehen also bei der Betrachtung des Klimas immer in eine längere Vergangenheit zurück. Trotzdem möchte ich heute vor dem Hintergrund dieses Gesprächs die aktuellen UAH-Satellitendaten herzeigen. Den Link dazu findet ihr unten in der Videobeschreibung. Professor John Christie und Dr. Roy Spencer ermitteln seit dem Jahr 1979 auf Basis von Satellitendaten eine jährliche globale Durchschnittstemperatur. Wir seitens des ICRs halten diese Daten für viel realer als die Hardgrad 5 Daten, die auf Basis von erdgebundenen und teilweise bereits inaktiven und weltweit verteilten erdgebundenen Messstationen zurückgeführt werden. Wir sehen also hier in dieser Grafik einen Rückgang der globalen Durchschnittstemperaturen in den letzten Monaten auf ein einigermaßen stabiles Temperaturniveau, so wie es bereits in den Jahren 2015 bis 2023 vorlag. Den Temperaturpeak 2023 und 2024 führen wir auf drei Phänomene zurück. Erstens auf die Hunger-Tonga-Explosion, zweitens auf ein El Niño-Maximum und zugleich 2024 ein sehr starkes Sonnenfleckenmaximum. Alle diese drei Phänomene sind gegenwärtig vorbei bzw. auf dem Rückzug. Doch darum soll es nur am Rande hier in diesem Video gehen. Vor diesem obig beschriebenen Hintergrund hatten wir die große Freude, mit Dr. Chris Barnes ein Gespräch zu führen, auf Einladung unseres ICR-Mitglieds Dr. Ernst Hammel. Danke an dieser Stelle ganz herzlich dafür. Er wird auch gleich Dr. Chris Barnes vorstellen und in seinen Vortrag und die anschließende Diskussion einführen. Wir, das ICR-Team, halten die Forschungen von Dr. Chris Barnes für herausragend, natürlich vor allem mit der Entdeckung der Korrelation der globalen Durchschnittstemperaturen mit der Bewegung der Pole und den entwickelten Theorien dazu. Ich kann mit Dr. Chris Barnes sehr übereinstimmen, dass der Klimamechanismus auf unserem Planeten durch einen mächtigen Antrieb, wie zum Beispiel durch den planetaren Geomagnetismus, geführt werden muss und die Treibhausgase dabei nur eine sehr untergeordnete Rolle spielen. Aber ich will hier an dieser Stelle nicht vorgreifen. Hier kommt gleich unser Gespräch. Das Gespräch wurde auf Englisch geführt. Es gibt daher zwei Videos, eines mit und eines ohne Untertitel. Das jeweilig andere Video ist unten in der Beschreibung verlinkt. Die deutschen Untertitel sind mir leider nicht sehr gut gelungen. Es ist mein erster Versuch, diese einzufügen. Ich bitte daher an dieser Stelle um Entschuldigung. Das nächste Mal wird es dann schon viel besser werden. Aber jetzt viel Freude und Interesse beim Vortrag und Gespräch mit Dr. Chris Barnes.
Good evening, everybody. I would like to welcome Dr. Chris Barnes this evening. Let me quickly introduce him and how I got in contact with him. Dr. Chris Barnes will tell us tonight how the magnetic pole shift we are observing and the climate might have something to do with each other. Yeah? And I do not want to give the talk of Chris, of course, just to remind you what we are talking about. Of course, it is well known that the magnetic North Pole is moving and actually quite rapidly over the last years and decades. Yeah, and it had always moved. And Chris probably will go a little bit deeper into detail. What is the reason behind it? But just to give you a picture, we see that the magnetic North Pole has been moving since the starting of the 20th century from a more southerly position to a more northerly position. Yeah? So there are several web pages where you can find this kind of movement uh, and can follow up, so to say, with the further uh, um, route of the magnetic North Pole. I think currently it's moving around 40 kilometers per year, something like that. I got in touch with Chris because I got interested in his uh, theory, more or less, that maybe what we observe as climate warming has a lot to do with this movement of the magnetic North Pole. Yeah. And he published in the meantime two papers in an open access journal. Yeah. It's this International Journal of Scientific Research, Physics and Applied Sciences. So I just want to give here the reference to these two papers. And yes, Chris also has a web page I found in the internet. So you can, if you're interested in his curriculum, you can find more information there and what he does besides climate research. So he has a lot of interests and you might be interested studying that. Yeah. Just by chance, in the recent months, there was another paper in a different field, but also a link to this topic published in Science Advances by a Chinese, I'm not sure where the other guys located, probably, uh, I don't know, exactly. I did check the uh, where the authors are really coming from. But the topic of this paper was, is there a strong link between the oxygen level and the geomagnetic dipole? Yes, of course, there is a link. Yeah, that's what they uh, observed, at least since the last 540 million years. Yeah, so this interesting, and this has nothing to do with what Chris will tell us, but just to see what's the content or uh, the finding of this group. Of course, we know the geomagnetic field can strongly influence the uh, ionization and the ohmic heating which arises from solar winds. Yeah, so energetic solar particles from coronal mass ejections hit the Earth, and depending on the strength and uh, uh, the alignment of the magnetic field lines, yeah, this can have an effect, yeah, on several observables. Yeah, it is also important, of course, for protecting us from extreme ultraviolet radiation because of their indirect effects, which I just will mention. But what turned out is that the oxygen levels really uh, are seem to be correlated to this geomagnetic field lines, yeah, magnetic field lines, in the sense that oxygen levels, yeah, increased actually, yeah, from uh, uh, parts per trillion, zero point 0.1 parts per trillion at the beginning, let's say a couple of uh, 2 billion years ago, yeah, uh, up to the more recent past, I mean millions, hundreds of millions of years, yeah, where the oxygen level, which has currently something like 21% by volume, uh, went up sometimes to 35% volume. Yeah. So this is something really astonishing. And 2.5 to 2.2 billion years ago, there was the so-called great oxidation event. Yeah? So that was the time when oxygen, reasonable amounts of oxygen were, so to say, introduced in the atmosphere. Yeah, we had almost an oxygen-free atmosphere before. Yeah, so and all this seemed to be interrelated somehow to the geomagnetic field, and you can imagine that the level of oxygen, yeah, has a big influence on the level of carbon dioxide. Yeah, because without oxygen, yeah, there won't be any carbon dioxide, basically, yeah, because there would be no plant life. Yeah, it is basically. So you need oxygen, you need carbon dioxide, both are needed to support life on the on this planet. So something must have happened, yeah, which allowed that the oxygen got released into the atmosphere, and that might have to do with the geomagnetic field. Yeah, and I'm ending with that right now. I don't want to go more detail with that because you will see the work of Chris. Yeah, is really, I think, a dramatic example how you can interpret global warming. Yeah, and how you can see other effects having more importance and global warming than the IPCC tries to make us believe. Okay, thanks. And Chris, it's yours now.
I'll just share up my screen, guys, and then we can get going.
Yes.
Okay, so I'm going to talk to you about Earth's magnetic climate. So I thought we'd have a nice spinning globe and some nice Earth lights to start off with. And what am I going to talk to you about? Well, in principle, all I'm going to say is that somehow, and I believe I found out how, that the moving dipoles, the north and south, in particular the north magnetic pole, but both poles are moving, that both of these somehow change the Earth's temperature. And the important point I want to get across is that they have changed the temperature in the past and that they are changing it right now, and that the process that's happening is an absolutely identical process. There might be a little bit of a top up on top of the process to do with a little bit of extra carbon dioxide, and I'll talk to you about that towards the end. But inherently, the major process is to do with the movement of the poles. So let's move it on. And I took this from the second paper, which is just a graphical abstract. And I think Ernst has showed you the first picture, the picture of the pole wandering about there, and how it round about 1620 or wherever, or it was at its more or less its furthest south, and it's gradually, no, sorry, 1850 or wherever, and it's gradually moved further and further north. It's not the most north it's ever been. The most north it's ever been is about 89 degrees north, which was in the peak of the medieval warm period. But right now we're at about 86.5. It seems as though it's actually slowed down, and it might be going back the other way a little bit, but we'll talk about that in a while. So the idea is, the summary of what I'm going to talk about is that the poles move, particle precipitation changes, which would have been Heinrich Svensmark's baby, but he was unaware of this massive effect of the poles moving. So when he wanted to look at the sunspot cycles and pick out differences between them, some of the differences were being masked out by this massive movement of the poles, which we'll talk about. So the idea is particle precipitation changes, the clouds will dissolve away, particularly the lower and the mid-level clouds. That lowers the albedo and the Earth warms up. And that is what has been observed very, very strongly by Ceres satellite data over the last 25 years or so. Now, I've been a bit dramatic here. I've said it's causing all recent warming. It's certainly causing a very, very big chunk of recent warming. And towards the end of the PowerPoint, we'll see what that chunk is compared perhaps to carbon dioxide. The new model is really, really cool because it predicts not only how this happens and how it accounts for our modern warming, but you can use it to hindcast and show up the presence of a medieval and a Roman warm period as well. Okay, now I'm going to gloss over this. I don't want to spend too much time talking about me, but I was fascinated by your background, some of you guys as physicists and electronics people. And I want to say I have a very similar background myself. So I started out life in the mid-1970s as a science of materials person, which basically in Bangor University was a bit of a mix of chemistry, physics, biological materials, electronic materials, you name it, even a bit of earth science thrown in and a bit of environment. So you more or less picked your own course units. It was a very nice course to do. There were only 6 of us chose to do it, so that was real fun. I then, at the back of my mind, I'd always fancied doing something to do with electronics. And as a practicing radio ham, I thought, well, I'll go over and I'll do a bit of electronics. So I went down to the same city, different building, and I did an MSc in electronic engineering, but with special reference to materials and devices, including some stuff on surface physics and physics of semiconductors, but also some stuff on microwave devices and goodness knows what else. So that was interesting. And then I was offered a PhD, and it was a question of, well, what they were able to get grants for at the time that was roughly on the materials side. And I found myself doing a PhD on effectively surface triboelectricity and surface states and things like that. So transfer of charge from metals to insulators. Anyway, I won't bore you guys about that any longer. Safe to say, of course, this is giving me a nice wide, even at that young, tender age, I'm getting a multidisciplinary approach. I'm appreciating life from all sorts of different angles. Eventually, after running my own research and consultancy business, after I did the postdoc and goodness knows what else, contracts got a bit tight and I looked for something to do, and it turned out I found myself doing some school teaching. So I then had a bit of a school teaching career, and I got involved as an examiner as well. So that's a summary of it. Hang on, sorry, better go back. Research fellow in ultrasonics then and quartz crystal sensors, multidisciplinary consultant for 30 years plus, school teaching for about 24 years. I filed all kinds of patents, and I've got all kinds of inventions, from biological inventions and blood analyzers and inventions to make plants grow better and goodness knows what else. But I've also been writing science as well. So I've been a lifelong academic author. So how on earth did I come to be interested in climate science? How come now climate science? Well, ever since like the late 70s, I've had a very, very keen interest in the weather, and I've kept my own weather records here in the UK. I started out life in university as one of those people believing that we were all going to burn to death. I actually believed that, somehow there was a lid on the atmosphere, and that we would boil up. And I remember having big arguments with some of the older, professors who were saying, oh, this is rubbish, it's just natural cycles and we'll all be okay. And here I am now at the same age that they were then, thinking, well, you know what, maybe they were right. Anyway, I've long suspected that there was something a bit wrong with climate models, especially the notion that CO2 was such a potent, I'm not saying it's not some kind of a greenhouse gas, it must cause some kind of a delay of heat leaving the atmosphere rather than a complete lid or a complete trapping. But where I live, we live right underneath a lot of air lanes, and I've been very worried about aviation cloud. I've been thinking that aircraft are having a huge effect on our climate, and particularly temperatures in the winter time are getting warmer and temperatures at night time are getting warmer. And it seems to me that the high cirrus clouds are much more of a lid on the climate than carbon dioxide, but that was the story. So that's when I began to read a lot about climate science, and I began to not only teach myself some of it, but try to develop some of my own ideas. So why this particular topic? Why the magnetic thing? Well, I did start getting a little bit concerned in 2022 when they said, oh, things are really taking off and we are going to burn. And, everybody said, well, this is crazy. This is the strongest ENSO there's ever been or whatever. I got a bit concerned about, recent reports accessing the warming models. I wondered if it was something to do with the Hunga Tonga volcano. Then I thought back before all this to the so-called hockey stick, and I thought, let's have some lateral thought here. And I thought, what else has got a hockey stick in it? And I thought about this movement of the northern dip pole, and I thought, could there be some sort of correlation here? And if there is a correlation, is there a mechanism that can go with that correlation? So this next slide is entitled Temperatures Past and Present. Am I not going too fast for you guys, am I?
No, not at all. It's okay. Fine. Perfect.
Cool.
No, it's great. A fantastic presentation. Thank you very much.
So I then think, well, let's think about the temperatures past and present. And it turned out that not only was there a correlation, but which seems to be working somehow better, it actually, when I took CO2 out of the model, it pumped up the size of the medieval warm period to a respectable size, to the size it says it should be in the history books. When I had CO2 in the model, it pumped it right down. And when I took CO2 out, it pumped it up. So I thought, how am I doing this? Well, what I'm doing is I'm using paleomagnetic data, and it's fairly sparse, but there is some available. The reference is St. Onge and Stoner, and it's in the paper anyway, but it's the only thing they show is a sort of a map of the globe with the positions marked on and the years AD. So I sort of interpolated every 50 years and plotted them out and stuck them into the model and hindcasted. And as you can see, you get the classic double peak medieval warm period. You get a Roman warm period. It's fairly weak, but I was reading a paper only the other day of someone who tried to use a big GCM climate model to hindcast these things. And that GCM model was also producing a very weak Roman warm period as well. So that's maybe the Roman warm period wasn't as warm as people think. I don't know, but that's possibly the only downside. But there is also an upside to that we'll come to right at the end of the presentation. Okay, so let's move it on. Now, I had to think about this business of I'm predicting temperature. I'm predicting a temperature here, and I'm predicting a temperature from a pole shift. Is that reasonable? Well, I did a Granger causality test, and I found that latitude leads temperature by roughly about 2 years. And then I'm thinking, well, how can this be? Well, okay, maybe it takes 2 years for all the clouds to move around the Earth, or maybe there's thermal inertia in the Earth and the surface of the oceans, or maybe, you know, there are cycles, you know, there's the ENSO cycle, which can take about 3 years, and there's the QBO cycle that's about 2 years. So I think it's reasonable. It's sort of, this bit's a bit hand waving, but I think it's reasonable to include it. Okay, so let's move it on. So it's no good if you don't have a mechanism, is it? So this is, I don't think it's the Antikythera mechanism, but it's some sort of it's probably an AI generated mechanism, but here we are. The search for the mechanism. The link to me would somehow be that particles are coming down into the auroral oval. And if the auroral oval shifts northwards, then, or shifts towards Siberia or something, then the place in the atmosphere where the interactions take place must also move. And I started digging around for some references on this. And I think the two most relevant references that I found were Anderson 2014, who discuss that energetic particle precipitation has massive impacts on mesospheric ozone. And then it couldn't have come at a better time, because this Sravastava guy actually published this right while I was writing the paper, and the paper would have been up the creek without the paddle, without Sravastava. And Sravastava publishes this paper, and it says, as the pole drifts, energetic particles get between 400 and 1200 kilometers higher in the atmosphere, and they move over towards Siberia, and there's a different pitch angle for these protons within this certain energy range. Now, then the final link is, how can this lot affect the clouds? Now, I know Henrik would have told us if he'd have been here, but I did a bit of research, and I found this business about energetic particle precipitation can impact cloud formation via the global electric circuit. And Tinsley and Dean did a lot of work on this way back in the 1990s. So I think the mechanism I have in mind is a combination of these three facets. Okay, so let's move it on then. Now, one has to say, okay, one has got a mechanism. Is that mechanism strong enough to create the forcing which is observed? So various people, and I'm not bothered to tell you guys about Nikolov and Zeller. I've had a lot of people, and by goodness me, they've advanced a bit. 20, they pick a spot the deliberate mistake. We've moved about 10, 20,000 years into the future or so. Anyway, perhaps my theories will be believed by then. But Nikolov and Zeller have made these satellite data which show that the albedos have been changing, and that's responsible for all warming in the last 20 plus years. Incidentally, they are not the only ones to have got this data. There are a few other papers have been coming out to suggest something similar. Well, when you make the calculations, and I won't bore you with the calculations, but they are in the paper, but when you make the calculations, it turns out that you can achieve almost this amount of forcing as the pole shifts from where it was to where it is now, and that translates to changes in the energetic particle precipitation. It's all in the paper. At my age, I don't memorize it all in my head, but I worked it out and it's there. So, okay, are you guys happy to move it on?
Let me just comment that, if I may, in our last paper, we also showed the series data, where you can see that the albedo changed over the last 20 years for locations like Vienna, but also the Egyptian desert.
Yeah, oh, so brilliant. Yeah. Brilliant. Okay. Cool. So, does it work across all latitudes? Well, I did the second study. This is the second paper I did, which was saying, let's try, first of all, with just the northern magnetic pole. Let's try and correlate all the data we've got across all the latitudes. Lo and behold, model versus what we observe, and it's pretty good, that, for just the northern pole. My guess is that what we observe and what we see there, the difference is probably the greenhouse gases, but we will talk about that in a little while. Now, here are umpteen different models. So I tested lots of other geomagnetic parameters all at the same time. So, oh, sorry, I need to go back on that. Okay, let me move your pictures out of the way. Okay, great. Okay, so I tested tilt only, which is the blue bars. I tested dipole moment only, which is the orange bars. I tested north magnetic pole latitude, which is the green bars. I did a two-pole model, which looked at the latitude and longitude of both the north and the south magnetic poles. And the purple line is what we observe. And as you can see, probably the best model there is the two-pole latitude and longitude model. The tilt only has a bit going for it in the northern hemisphere, but not so much the southern hemisphere. The model and the observed come together very, very well in the Southern Ocean, round about the South Geomagnetic Anomaly. Whereas the biggest difference is in the northern mid-latitudes, where you've got all the pollution and you've got all the aircraft and you've got the carbon dioxide. And there is also a sizable difference up at the North Pole as well. So the two-pole model scores best. The EEP warming works out at about 250 millikelvins per decade, and about 2.5 times that in the northern polar regions. Okay, let's move it on. Now, all of these models, and this really brings it into context to show that, you know, this is not a crank theory. There has to be something about this, because all of these models are showing we all have got coefficients which show an inflection at the South Atlantic geomagnetic anomaly. And I find that absolutely amazing, because we know that the energetic particles come plunging right in. I mean, that's why, you know, ships go missing in the Bermuda Triangle or what have you. Yeah, and it's absolutely, it's all here. So you can see how the regression coefficients are getting really strong at the poles. You can see how they're inflecting at the geomagnetic anomaly. And in fact, at the geomagnetic anomaly, that is where there is least warming. In fact, the clouds are normal. If you go to the southern hemisphere, the clouds are far more normal than the northern hemisphere. Okay, let's move it on. Now, obviously, you guys are interested in doing some CO2 work. Clearly, there are other drivers. So what I have tried to do here is I've tried to look at the residuals from this model, and I've tried then to regress them against the other drivers and see what was what's affecting what, really. So I looked at carbon dioxide, sulfur dioxide, aviation, solar cycle, and this is a strange one, but I'm sure Martin might appreciate it. World electric power. Now, why on earth world electric power? Well, I had this inclination that the power grid radiates energy, and it radiates that energy and it affects in some way the energetic particle precipitation. I found a paper which shows that the powerful VLF transmitters on the Earth that are used for submarine communication and used for experimentation in the upper atmosphere, you know, things like the HARP and the Sura and what have you, actually affect the Van Allen belt, so the particle precipitation. And I thought, well, if they're affecting it, I bet my bottom dollar that harmonics from the power grid could affect it as well. And it turns out that there is a small but perhaps ever-growing effect there, but we'll have a look at that in a while. When I plotted the residuals against CO2, the correlation was extremely weak. It's, you could say, statistically irrelevant, but as you go to the poles, there's more of it. So, but before we get to CO2, let's just have a look at SO2. Oh, hang on, sorry, I've gone too far. So if we have a look at SO2, now, the traditional climate science people are getting all excited, aren't they, about SO2, because they've realized that it was cooling the planet. But my guess is it wasn't combating CO2 so much as it was combating the pole shift. Of course, it peaked around about 1990, and then we started having all these clean air acts, and then we started making ships stop using dirty diesel and goodness knows what else. And maybe we're paying the price for that, because as you can see, there is a statistical, it's a weak statistical relevance, but nevertheless, SO2 definitely does cause some cooling. Okay, so now we move it on. Aviation. Well, I look up at the sky, and the skies, and you're all the same, mate. You're you know, older guys, you know the same as I do, that the skies don't look the same as when we were kids. And I look up at the skies and I think, well, all that mess up there must do something. There are tens of thousands of papers about aviation, and they can't make their minds up. Some say it's cooling, some say it's warming. You've got these idiots now that want to geoengineer by using ordinary aircraft. They think that they think that if they make contrails, it's going to cool the planet. Well, I would beg to differ. I would say the more contrails you make, the more it's going to warm the planet. And although that's only a very weak statistical evidence, nevertheless, the slope is positive. So I'll rest my case there. Okay, let's moving it on. Now, this is sunspot number, average smooth sunspot number across the entire period. So obviously there's you can obviously see the cycles, you can see the oscillation in it, but people for part of the period, the sun was getting more active, and I think we can see that there is an effect of there is a solar effect there. Now, again, if Henrik was here, he'd probably be able to talk to us a lot more about this effect than I can, but I thought it was worth including. So Henrik's not here to support me or to shout me down or anything, but I'm sure he'll have a look at it when he's better. I thought, well, is there a link with what he did? And this is my take on the link. Solar proton events and galactic cosmic rays are the main sources of energetic particles. The solar cycle galactic cosmic ray effect varies from cycle to cycle, but sadly, it has been strongly skewed by our magnetic EEP effect. And of course, Henrik would have been unaware of that at the time. And all these people that were running him down would have been unaware of that at the time. So maybe when he's better, he can piece together what he did and what I did and come out with something absolutely fantastic. Okay, let's move it on. Electrical power is a very odd contender, but I thought it was one that might, and it's a very, very weak correlation, but no one really knows what's going on with the Van Allen belts, but we do know that there is more warming in northern mid-latitudes. And although this is very weak, it suggests that it's causing 14 times more warming than carbon dioxide in the northern mid-latitudes. And I said, why should this be? Well, there is one reference that suggests, I think it's Pronenko 2014, suggests that power line harmonic radiation is parasitic radiation from the power supply, which enters the ionosphere magnetosphere system and can impact upon the electron population in the Van Allen radiation belts. So who knows? And maybe there is a very strong case, not just for using, well, solar power, but for using off-grid solar power. Anyway, let's move it on. So here are the conclusions. Our moving magnetic poles presently change Earth's temperatures and climate and have done throughout history also. The said change is likely through the energetic precipitation particle height and position, which modulates and reduces clouds amounts and hence albedo. It accounts for huge amounts of warming on the planet. Long-term solar cycle changes have been harder to show. Further regressions of residuals show statistically weak or very irrelevant trends of positive for CO2, negative for SO2, positive for aviation, and positive for electrical power. Now, at the time of writing, that was as far as this went. But since Ernst has asked me to do this, I've actually written a third paper. And I'm just going to show you a little flavor of what is in that third paper. So here is a flavor of the third paper. and it's got some Romans, and it's got some medieval people, and it's got some factories and smoke and chimneys. And basically it says the dip pole moves and the planet warms. The further north it moves, the more warming we get. The effective slope. And what I've done here is I've looked at data which was out there. Basically, I think it's NOAA or NASA data. I looked at some of their plots of what they say the Roman warm times were like. So I've not looked at my own model. I've looked at independent data, and I looked at the slope between the top of the Roman warm period and the top of the medieval warm period. I calculated that slope in terms of degrees of pole shift, and that slope turns out to be 67 millikelvins per degree. I then looked at our modern warming, and the slope of our modern warming is 74 millikelvins per degree. And I then suggest that perhaps the difference is due to greenhouse gases, and perhaps predominantly CO2, but there could be others in there as well. And that this will allow me to make some kind of estimate of climate sensitivity. Okay, so what have I done next? This is fascinating. Okay, the two weird yellow blobs that don't fall on the line on the large part of the diagram on the top left, that is the X2 plot. That is the pole shift plot. Can you see what's happening? They are the yellow blobs generated by the medieval warm period and the Roman warm period. And the slope is more or less parallel to the slope for modern warming. Now, if we were to say, what would CO2 do? Well, hang on. What would CO2 do? Well, it'd look silly, wouldn't it? So if we try to plot the two on the CO2 plot, which is the X1 line plot, and we try to fit in the Roman warm period and the medieval warm period, they've only got about 6 parts per million of CO2 between them, and they would look absolutely stupid on that plot. So I think I more or less rest my case. When you run it through a multi-regression analyzer, it tells you that both are significant drivers. And there is the regression analysis. X1 is carbon dioxide. So you multiply that little tiny number by the ppm. X2 is the pole shift. So you multiply that by the pole shift. And when you do that for modern warming, it tells you that you've got something like 750 millikelvins or 0.75 of a degree due to the pole shift, and about 0.35 of a degree due to the carbon dioxide. Now, I've had to play around with this algorithm. I haven't logged it down, but I'm holding a piece of paper here with some other results on. I had to play about with 260, 280 for the difference between the two historic periods, 280, 300, 260, 300, and it doesn't really matter what you do, you still get the same two ballpark figures for the carbon dioxide and the pole shift. So you're still saying that the pole shift is by far the stronger of the drivers. You can see that they're both pretty powerful regression coefficients if you look at the X1 and the X2 there. Okay, so I think hope you've enjoyed yourself, guys.
Definitely. Thank you, Chris. It was fantastic. I
Very
would,
interesting.
yeah, it's not only very interesting, very stimulating actually. I wonder, this is my first question, how was the reaction of so-called climate science to these papers?
They don't like it. they they don't like it, but they can't answer it. But I have spoken to a gentleman who is a retired chemist, a reader in chemistry in our local university. I won't mention his name because he is very nervous for political reasons. But he agreed. He says, "Do you know what, Chris? You have found a new driver." And he says, I do agree with you. He says, I used to teach this stuff. And he says, he says, same as you guys. He says, there is an effect, but it's not as strong as people make it out to be. But
Sorry, Chris, can you stop the presentation?
I can, yes.
Yes, thank you. Then we can see you. We can with a better look to you.
So,
sorry
to have
you.
international response to your paper. So I understand that the local response is maybe biased somehow because people know you, and but is there any international response? Did you get any comment?
You are the only. Do you know what? You are the only. Apart from cranky journals wanting to republish my work, you are the only person that has contacted me.
Okay.
It's unbelievable.
It is unbelievable.
Chris, I have a very...
I will say one thing. I don't know if you know anything about our politics in this country and about what's going on with them wanting to spend billions on green technology because they want to sell it all around the world and make money. But it's interesting. I contacted members of the opposition political parties, and they are very excited by the work. So I guess they are going to run it past their scientific advisors. But I contacted the leader of our Conservative Party and the leader of the Reform UK Party, and they are incredibly excited by the notion that, maybe things are not as bad as we thought, and perhaps we can carry on and exploit some of our other, our traditional energies. And my feeling is, if you look at those graphs, the mistake we made, even in combating any warming, whether it comes from pole shift or carbon dioxide, the mistake we made was when we stopped burning coal on our fires. When we were young men and we looked up at the clouds and they were lovely, big, fluffy white clouds. And my feeling is it's the coal smoke that was nucleating those clouds, because they are not there anymore. And the sulfur dioxide and the sulfur aerosol is gone. They're wanting to pump it into the upper atmosphere, and I believe it should be lower down in the atmosphere.
Dear Chris, I have a very, very, very important question to you.
Uh-huh.
How to tax the pole shift?
Wow, I wish we could. We could make a lot of money, couldn't? But when it comes back the other way, we get the money back. So maybe it's just an investment bank, I guess.
Great, yeah.
So, but
answer.
Is this maybe the reason why your research is not so
popular? Yeah.
So people are not so interested in your research?
It could be. Yeah, it could be. But this is political, isn't it?
It's terrible.
It is.
It's absolutely terrible.
It's a shame because you ask the question, what the criticism here is that because of the multicollinearity, someone could say, okay, the pole shift clears the clouds heat the oceans outgas more CO2, it's going to get hotter and hotter and hotter. If that's the case, why didn't the oceans outgas all that CO2 in the medieval times? Why did the CO2 stay stable? And when you look at the Munalona graph, the CO2 on the Munalona graph goes in, out, in, out. So the ocean is sucking it in, and then the heat is sending it out, in, out, in, out. So that is why there is the correlation with the pole shift. It's not, so the pole shift is the main driver. And this is what I want to try. I'm sure you guys have understood that. Because of the lag, you can see the lag in it.
Absolutely.
We don't have real valid direct data about the CO2 content in the, let's say, medieval warm period. Yeah. So, well, we have the ice core data from Greenland, which are more recent.
Yes.
But they all are just average data. They are not year by year. Yeah. Data.
Yeah. I see what you're saying.
So we have only proxy data, more or less. Yeah. So this part is not completely answered, after my opinion. Yeah. CO2 content was really in these times. Yeah. Because we have average data over a long period.
I understand. So you're saying we don't really know for sure. Did it in, out, in, out?
Yes.
Yeah. Or by how much did it in? Yeah, but my guess is at the end of the period, if you look at the medieval warm period, it lasted rather long. I mean, it lasted long enough. You would have thought that by the end of that period, there would have been large accumulations of CO2 in the atmosphere. Why do we not see that in the ice cores? Are we saying that the sea was capable of taking those large accumulations immediately back again, but the sea is not capable now because we're just pumping willy-nilly more and more into the atmosphere? I mean, you see where I'm coming from?
Yeah, of course. Yeah, so the equilibrium was disturbed. Yeah. Right, or is disturbed right now. But if we don't see CO2 as the main driver of the climate, this would not matter so much. Yeah. So
this is what I'm I think this is what I'm hoping to see, and it's early days yet because of the 3-year delay. But what I would expect to see is a stabilization as the pole now is moving back south. We would expect to see a stabilization. Now, if you do the two plots, if you do the pole shift plot, you see it's starting to curve over and stabilize. If you do the CO2 plot, you just see it going absolutely crazy.
Yeah.
Now, one has to be true, and within the next 2 years or so, I think we will really know. One of the problems is that I only plotted the work until 2020. I purposely did not go beyond 2020, knowing about A, the Hunga Tonga, and B, the ship's, the ship fuel business.
Yeah.
You've got a knock-on effect from both of those. But reading, I'm not an expert on volcanism, but reading up about what I've read about volcanic activity and the climate, many volcanic eruptions cause a warming of 2 or 3 years, followed by then about 6 or 8 years of dramatic cooling if they are the big, very big eruptions. So maybe this will follow. And then you've got the problem then is it the volcanic eruption or is it the pole shift? But
well, the Hunga Tonga was like slightly different because it was mainly water vapor. Yeah. So there was not a lot of dust.
Not a lot of SO2 and not a lot of carbon. So if it's water vapor, my guess is it's just going to cause a couple of years of warming and then end of.
Yes, that we see that already actually in the satellite data. Yeah.
Yeah.
So it's falling already. Yeah. If you look at the University of Alabama satellite data, you see already the falling trend in the temperatures, in the global temperatures. Yeah.
Yeah, yeah. Okay. Well, if it's falling, that's good. That's good news. And maybe we compare notes in 2 or 3 years' time. Maybe we'll be in the freezer by then. Who knows? I wrote another paper. I just on my website somewhere some years ago when I was looking at the length of different solar cycles, and I noted that when you have you get these strange effects when you have either a very short solar cycle or a very long solar cycle. And I noted that we get here in the UK, we seem to get the hottest summers and the coldest winters about plus or minus 2 years from the solar maximum. So who knows, in a couple of years' time, we might get some really, really cold winters. Who knows anyway? And any more questions, guys? Because I'm just about exhausted.
Yeah. Well, one question I have, definitely a technical question. If the pole shifts to the north, towards the north, are we talking about a more drier atmosphere in the north than in the south? Yeah, the humidity in the south is definitely higher than the humidity in the north. So if you have, so to say, the magnetic precipitation in the north, then you have less humidity available in the atmosphere for cloud formation. Than you have in the more southern position.
Yes, that's another. Yes, that's. But I mean, the initiation process is much high. The initiation process is way up in the ionosphere. It's what drips down. It's the chemistry and the physics that drips down. But
secondary effect.
The secondary effect would be humidity dependent. Yes, I take your point there. Yeah.
Chris, you looked at the movement of the pole. Did you also look at the change in the strength of the magnetic fields?
Yes, I think one of them considers the dipole strength. I'll just bring up the. I think I did look at the. Let's just. Where is it? Dipole moment. Here we are. Can we see the slide? Okay.
Can you share it?
I'm not sharing. Okay, hang on. Let me just share up the screen again. Right, where are we? Okie dokie. I'm not full screen. Can you make that one out? The dipole moment is the orange bars.
Yes.
Okay.
So yes, there is some correlation, but it's not quite so strong, but it is in there nevertheless.
Okay. So the strength of the magnetic fields only weakens a little bit the last centuries. So maybe that's one of the reasons. But that effect, you cannot see that.
Yeah, I think so. I mean, the strength will affect the magnetic reconnection. I think perhaps it's the position that the precipitation takes place is perhaps more crucial than maybe the strength, because of course the strength of the sun, the interplanetary field is also changing, as well as the dipole moment, and that's something I haven't considered.
I see. Thank you very much. And my last question is, it was very interesting for me to hear that you also consider effect of power supply lines.
Uh-huh.
You are right. That was very interesting for me. Um, uh, you know, the EXH vector is the so-called pointing vector,
Yes, yes,
and the um, pointing vector shows the direction of the energy supply.
yes.
Um, and of course, along the movement of the
Power
point
Yeah.
vector, there are losses. So so do you consider the losses which make an effect?
Mm. It's not something I've considered, but yeah, certainly there are losses. Certainly there are huge losses to space from the power. I mean, you can detect power line harmonic radiation, and it actually affects things like the chorus frequency. It affects it affects all sorts of frequencies from that you pick up from space. So yeah, I guess so. I mean, I actually reckon that I reckon I've actually picked up harmonics of the. I've played around with I've played around with Spectrum Lab and antennas and things, and
Yep.
I reckon I've picked up harmonics of the US power grid and stuff like that. So yeah, I'm sure that you're getting all sorts of interplay between the UK and the US power grid and the harmonics and goodness knows what else.
Okay.
I have two last questions. I hope they're the last questions. First, to the last top, referring to the last topic, the global power grid, if you like, yeah, or the global electric power consumption. I mean, you considered only the radiation as a possible source of uh, uh, disturbing, let's say, the uh, atmospheric uh, uh, cloud
Yeah,
formation
yeah. Were you going to
situation.
say why didn't I consider the carbon dioxide? Are you?
No, 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 no.
Oh,
What I would like to know, did you consider the thermal power generated by
by
uh,
the power lines themselves.
yeah, by the power lines, by the power consumption, yeah.
Yeah. Now, I did write another. I have written another paper which I've not published yet, and
Yes,
it's called Why do climate theories fail? And it's got a lot of stuff about the thermal power. It's got a lot of stuff about waste heat.
yeah,
And
exactly. Yeah,
when they're talking to us about urban heat islands, and they're saying
yes,
all this stuff about the sun warms up the concrete, and that is an urban heat island. And I am thinking, well, goodness me, everything has got waste heat. The electricity supply industry, everything that we are doing now
yes,
is generating waste heat. And even if you forget any heat trapping by any greenhouse gases, the planet has got a relatively fixed adiabatic lapse rate.
yeah.
And if you start off with temperature A at the bottom and temperature B at the top, and the difference is relatively fixed, then the bottom will warm up somewhat due to the waste heat alone.
Exactly. Yeah. So that would
Yes.
be a nice consideration. And the second question has to do with the possible pole shift flipping. Yeah, that if the we had in
Yes.
history we had
I don't think we're due for a. I
no
mean,
no 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 I'm not saying that, but
no.
we had in history, yeah, in the
Oh yeah,
past we had such situations,
yes we did.
and
Yes.
that must have had influence on the climate. And there is some indication, I think, something like, I'm not sure about the exact number now, like 30 or 40,000 years ago. There was some.
41,000. It's the Lachon thing, isn't it?
Exactly. Yeah. And you see it in the temperature curve, actually. Yeah.
Yeah. Yeah.
In the ice cores. Yeah.
Wow. Yeah. Yeah. Oh, there would be phenomenal effects, wouldn't there? Because if you know, all the clouds in the middle would go haywire as well as the clouds.
Exactly. Yeah. Yeah.
Yeah. Yeah.
Well.
Okay. Any more for any more? Oh, I see the cat's back again.
I was always there listening.
Cool.
Dear Chris, I hope we can keep in touch.
Me too.
And we can exchange our research. And of course, you are all the time invited in our regular meetings we have. It would be a pleasure for me, and I hope for all other guys.
Definitely, yeah.
If you
how often are you having meetings?
If you would join our groups of independent climate research.
Yeah, we meet every 2 weeks on Tuesday at this time, more or less. Yeah, but you should not be obliged to. If you want to.
Maybe I drop in now and again.
Yeah, exactly. Yeah, so if you just notice that every 2 weeks, yeah, we meet here, yeah, and at about the same time, and we exchange our findings, and sometimes we are much more, yeah.
Right.
Well, now it's summertime, of course, it's always a problem, yeah.
Yes.
But maybe next time we are twice as many, yeah.
Okay, cool.
As a forecast, I will send this information. That's one of our sayings. Here is the logo of ICR.
I think maybe I've seen this logo on. I think I've seen it round. Maybe I've seen it on Twitter or something like this. You know.
Mm-hmm.
Okay.
I will send you this chart.
Oh, fantastic!
This picture by email.
Yeah, yeah. Okay. Well, I'll try and say a little bit of. So I'll say Dankeschön and Guten Tag. Auf Wiedersehen.
And we say thank you so much. It was really great. And also in the name of all our group members, please let's keep contact. Let's keep in touch. I think we have some important messages. That's what I would like to claim.
Indeed, 100%.
Okay.
Thank you.
Thank you so much.
Bye.
Bye. Bye.
Thank you. Goodbye.
Vielen Dank an dieser Stelle nochmals an Dr. Ernst Hammel und Dr. Chris Barnes. Sehr geehrte Damen und Herren, liebe Freunde, ich freue mich auf euer Feedback. Ich freue mich auf eure Fragen, auf Deutsch oder Englisch. Auf Englisch werden wir sie auch an Chris Barnes direkt weiterleiten. Und ich freue mich auf die Diskussion, die jetzt unten beginnen kann. Alles Gute und bis zum nächsten Mal.